So in the previous video, we saw that there are several different types of orbitals at different energy levels that an electron can occupy. And what we're going to do here is look at and rank the energies of all those different orbitals that we talked about. Now, the relative energies of the orbitals largely depends upon what type of system we're working with. So either we can have what's called a single electron system, which is much like a hydrogen atom, or a multi-electron system. Okay, so let's look at the single electron system first. Okay, so when we have only one electron and it's trying to decide which orbital it's going to occupy, these are the choices that it has. Okay, the lowest energy orbital is the 1s orbital. Okay, above that in energy is the 2s orbital. But it turns out that the 2p orbital, with its 3 suborbitals, are going to have the exact same energy as the 2s orbital. Okay, next up from there is going to be the 3s orbital, which is going to have the same energy as the 3p and the same as the 3d with its 5 suborbitals. Okay, and then from there we get to the 4s, okay, which, as you can imagine, is going to have the same energy as the 4p and the 4d and the 4f. Okay, so in the case of a single electron system, the relative energy is mostly dependent upon the principal quantum number. Okay, so it has nothing to do with the shapes of the orbitals or anything like that. Okay, so that's for a single electron system. In a multi-electron system, things are a little bit more complicated. And that's because once you start putting an electron on the atom, that's going to change the relative energies of the orbitals. In other words, if 1s is the lowest energy orbital there, the moment that I put an electron into that 1s orbital, that's going to create repulsive forces that are going to change the energy of the 2s orbital or the 2p orbitals. Okay, so this has a lot to do with the shape of the orbitals and how they interact with one another. Alright, so what we find is that the lowest energy orbital is still the 1s orbital. Second is going to be the 2s orbital. Okay, and then the 2p orbital is going to be above that. Okay, the next one up is going to be our 3s orbital, which is going to be higher in energy than the 2p, followed by the 3p orbitals. Okay, so you can see 3p is higher in energy than 3s. Now we might expect that 4s would be the next one up, but because of the way that the orbitals interact with one another and the effect of having electrons in the orbital, it winds up that, actually, I should say, 3d would be what you would expect. 4s is what you actually get. Okay, so we would have expected to fill up the third energy level before moving to the fourth, but it turns out the 3d orbital with its 5 suborbitals are higher in energy than the 4s orbital. Then after that we have the 4p, which I should probably draw with the other p orbitals. Okay, so these are the relative energies for the first few orbitals. So we can see that the 1s orbital is lower in energy than the 2s, which in turn is lower in energy than the 2p, which is lower in energy than 3s, which is lower in energy than 3p, which is lower than 4s, followed by 3d and 4p. And I think what you're seeing here is that it's rather complicated to try to remember what these orders are going to be in terms of increasing energy levels for each one of the orbitals. So there's a couple of different ways of doing this. One is to abide by the m plus L rule. Okay, so let's say you have a 5s orbital. Well, whoops, it should not be the m plus, it's the n plus L rule. Okay, so if you have 5s orbital, 5 is the value of n. Because we have an s orbital, that means L is going to be equal to 0. So that's going to equal 5. If we compare that to, say, a 3p orbital, okay, here we have an n equal to 3. And an L, that is going to be, well, let's see, we have a p orbital here, that's going to be a 1. That's going to be a 4 total, which means the 3p orbital is going to be lower in energy than the 5s. Okay, that's one way to do it. The other way is to follow Madelung's rule. Now it's important to note that Madelung's rule, there's no reason why it should work, it just happens to work and it serves as a mnemonic. Okay, basically what we do here is we start off by writing out the different orbitals in each one of the energy levels. So first we start off with 1s, and directly under 1s we put 2s and 2p to the right. Okay, we know there's only an s and a p orbital in the second energy level. We move to the third, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and 5g. I'm going to stop there because we really don't need to go much higher than this. Then what we do is we draw diagonals. Okay, and we kind of imagine going around in sort of a spiral here. Okay, and that will give us the order of our orbital energies. Okay, so you can see here we have first the 1s orbital, followed by the 2s, goes around to 2p, to 3s, all the way around to 3p, to 4s. You can see here where we skip over the 3d. Then we come around to 3d, then 4p, and 5s, and so on. So those are the two different ways of determining whether or not, or whether one orbital is higher in energy than another. Okay, now this allows us to set the order of the orbital energies. In the next video, we'll look at how we can, a much easier way that we can express the positions of electrons in an atom.